that then.
Yeah.
Mhm.
Cool. And one last thing, I don't know if Amir made us live already because he sometimes does that without telling us. We can use, okay, we're live. I was gonna say we can
Yeah.
use the little chat on the right-hand side to coordinate if we want.
Okay. Um, chat. Oh yeah. Okay. There's a chat, right?
Yeah. Cool. Okay, I guess let's
All
get
right.
started. So hello everyone, welcome to another episode of Deep Random Talks. Today we have Andre here. Amir is hiding in the background because he is somewhere where the background noise is just too loud. But you can interact with him in the chat if you want. So yeah, Andre, we always start these sessions by just asking like, what are you drinking? Are you drinking anything right now? I have a jar of warm water. You can see my face through it.
Interesting. So I have two things. I also have a jar of water, but it's cold.
Mm,
And it
nice.
looks very similar to yours. But primarily I'm drinking coffee in
Okay,
my thermos mug. Mhm.
nice.
Yeah, I absolutely need my coffee.
Yeah. Yeah, I'm always kind of trying to drink less, but I do really enjoy the ritual of coffee.
Hmm. Yeah,
Yeah.
I've been told many times I should drink less coffee, and I probably should, but
Hmm. Yeah, actually, during my master's, which is relevant to this conversation because I studied geophysical fluid dynamics and ocean modeling, I decided to
hmm
stop drinking coffee for some reason. I think I was just like reevaluating my life, stop drinking coffee. And I remember one of my colleagues in the math department coming up to me one day and saying, Serena, you seem unwell. And I was like, what are you talking about? I'm fine. There's nothing wrong. And I realized that he was just picking up on my severe caffeine withdrawal that I experienced for like a few days. Pretty awful. Um, anyways, so today we're here to talk about a paper by DeepMind called, well, I can't actually remember what the paper is called. Andre, can you remember?
skillful precipitation nowcasting using deep generative models of radar.
Okay,
I just
cool.
read this.
Yeah. So essentially, they're using Gans to do nowcasting, which we'll definitely talk about. But first of all, and Andre, do you want to just introduce yourself quickly?
Yeah, sure. So, yeah, where do I start? So my background is in atmospheric modeling and atmospheric science in general. So I first started an undergrad in physics, but I was always interested in the atmosphere. And then later I discovered that you could actually study atmospheric science, and so I did my master's in meteorology, so which is essentially the science of weather forecasting. Um, and it's actually a lot more scientific than most people would probably think. Most people in meteorology are physicists or chemists. Um, and it's very computational, so it's a lot of high performance computing. And we'll get a bit into that, but weather forecasting today is mainly done based on physical equations and solving them numerically. Um, and but also involves a lot of radar and remote sensing and satellites and all of this, which is all really cool stuff that I love, and that's why I went into abstract science, right? Computing, radar, and all this cool stuff, and fluid dynamics as well. So, and so when I finished my master's, and that was back in Germany, so I'm German, so I did my education up to my master's in Germany. And then I wanted to go abroad, and I applied to U of T, and I got into the physics department at U of T. And first I started working on so very idealized atmospheric dynamics, like stratosphere troposphere interaction and turbulence. But then I got more into regional climate modeling, and with climate change at that time becoming way more important, and water resources, and so I started studying climate change impacts on water resources using high resolution simulations, climate simulations. And then for my postdoc, I started working for a hydrological consulting company, and I still work for that company, so it's Quanti. And there I looked at climate change impacts on groundwater and surface water. And what I do now is climate change impacts on water resources, primarily still regional climate modeling. I still work with folks in U of T. But what we also do, and this is sort of going back to my background in weather forecasting, is real-time hydrological forecasting. And hydrology is really driven by the boundary conditions, and the dominant boundary conditions is the atmosphere. So rain to a large extent, but also evapotranspiration. And so we use weather forecasts, numerical weather forecasts, to force our hydrological models, which are also numerical models, also based on physics, in a very similar way as the weather models. And so it's a lot of it is about coupling different physical models, right? And downloading a lot of data and running it operationally, sort of in a real-time pipeline, and then producing forecasts. Yeah. We don't use radar though, because for the most part, radar is not predictive, right? Yeah, you can add a little bit, like we discussed today, to make it slightly predictive over a short time period, but we are looking at longer time periods, right? So we're looking at a couple of days up to sub-seasonal 30 days. And for that, radar is not that useful.
I guess, yeah, DeepMind will, or argues in their paper that radar is actually useful. So that's pretty cool. I guess like getting into it, yeah, like I'll, yeah. So DeepMind, they created this tool called DGMR, which I think is Deep Generative Model of Rainfall. So they say that this method accurately predicts the likelihood of if it's going to rain in the next 5 to 90 minutes. So this is nowcasting. And yeah, supposedly this is one of weather forecasting's toughest challenges. So I am fairly well versed in this. As I mentioned, I did my master's in geophysical fluid dynamics, focusing on ocean modeling. And I always thought that was very cool how you can represent ocean flow. And the ocean makes up like 70%, I think, if I remember my stats correctly, 70% of like the world.
The Earth's surface.
And yeah, the Earth's surface. And physical equations like the Navier-Stokes are able to summarize the flow of the ocean. It's pretty cool. And this is how I kind of think about physical equations and the Navier-Stokes in general. It's really F equals ma, so it's Newton's second law. You have your force, and then you represent that force somehow, and you can get more and more detailed, and this allows us to really understand physical systems, and this understanding is backed off of hundreds of years of study and science rather than backing it off of, let's say, like data and learning data distributions. But yeah, how do you think of that, Andre, this idea of like F equals ma, that's all it is? Like, is that like a fair representation?
Well, for the fluid dynamics, yes. Of course, there's a continuum extension of that, right? But essentially, that's really all what the Navier-Stokes equations are, right? It's momentum transport and mass transport. But then there are a lot of other effects that you have to consider that make the cloud systems in particular very complicated. Right? So if you're just looking at aerodynamics, there's one component that you do need to represent that is hard to capture, which is turbulence, right? And that is often represented by some kind of viscosity or like eddy viscosity or something, right? So yeah, just add some diffusion term. There are other ways of doing this, and there's actually very interesting machine learning ways of doing this now. But this has been a long-standing problem in the ocean also, to really in a very similar way, right? In the atmosphere.
So in terms of these like different representations, one that I always really struggled with, and I still think I don't quite understand, is vorticity, which I think is something about like some sort of turning motion, just to like indulge myself. Like, can you explain vorticity? Is vorticity important to what we're talking about with weather forecasting?
Right. And so it's related to angular momentum conservation. And yeah, so what is vorticity? It's vertical motion of the flow, as the name suggests. You can, and I think it's called the Helmholtz decomposition, but you can decompose a vector field. So a flow field is a vector field. Right? You can decompose it into a potential function and into a stream function. And in engineering flow aerodynamics, that's usually potential flow. And also, for example, groundwater flow is completely potential flow. So you can, essentially the flow direction is following the slope of a potential function. And this is a very good approximation in many cases. In geophysical fluid dynamics, it is dominated by rotation, so the Earth's rotation. And so you can describe almost the entire flow field actually by a stream function, which is similar to a potential function, but the flow is perpendicular. So this is essentially from the Coriolis force. So the Coriolis force tends to divert everything in the northern hemisphere to the right. And so instead of following a potential function sort of along the gradient, it actually follows in the right angle of the gradient.
Right,
So
and the Coriolis
along the
force is
topographic
responsible for
lines,
like
right?
different ocean
Yeah.
flow, also why our toilets flush and flush
Exactly.
to the right in the northern
Yeah,
hemisphere, I
yeah.
think.
And it's similar in the atmosphere as well. So the atmosphere and the ocean are both extremely dominated by vertical flow or rotation because of the Coriolis force, because of angular momentum conservation from the Earth's rotation, right? And so in this sense, it's very different from engineering flows that you typically look at, and this, also because of the scale, right?
Mm-hmm.
So the dominant quantity that, if you want to describe the flow field with one quantity in geophysical fluid dynamics, it's vorticity. Whereas in engineering flows, it's usually the potential flow and
Okay.
groundwater as well. But
Yeah. So it really just seems like, and thank you for that clarification. Sometimes I wish that I could go back and redo my master's studies, and I think I would have enjoyed it a lot more when actually trying to learn rather than just like finish for the sake of finishing. But anyways, it really seems like, so to do weather forecasting or climate modeling broadly, there's a lot of physics that you really need to understand, and a lot of like just things about the world and how the world works, like Coriolis effect. That is something that I don't think many people in machine learning have to even think about. And what's really cool about this DeepMind paper is that they take a machine learning lens on this weather forecasting problem and like really fit in the spot where there's a need for new methods. Because my
right.
understanding is using these physical models, they aren't very good at like nowcasting because there is time, like there's the spin up time
Right.
where these models have to, based on like the initial conditions you give it, it needs to take time to like reach that steady state. So you can't make predictions within like the 5 to 90 minutes very easily.
Yeah. So the issue there is really that weather forecasting is an initial condition problem, right? So it's really dominated by the state at which you initialize the forecast, and then if you knew the state perfectly at any point, and then you could take the equations at sufficiently high resolution and just calculate it forward, that would actually work really well. The problem is we often don't actually know what the current state of the atmosphere is, or our knowledge is very incomplete. And so the shorter the time is that you're forecasting, the more it's dominated by the initial conditions, right? And the more precisely you need to know them to make a good forecast. And so we are estimating the initial conditions, but only with very limited accuracy. And this is just because of limited observational networks, right? And so if you're looking at a longer lead time, meaning is the time that you're forecasting for. So if you're looking at a couple of days, a lot of the small scale variation is already sort of diffused and forgotten, and it doesn't affect the general probability distribution of the forecast as much anymore. But for very short range forecasts, that's absolutely critical, and we often just don't know it. Interesting though is that there are some observations, like radar, for example, that can give a very accurate picture also of current conditions, right? So of the precipitation field. At the moment, it is, from a physical technical perspective, difficult to assimilate these kind of data into the physical models and then use them for direct forward prediction. So data assimilation in this sense is an important part, and that is data assimilation is the process of getting all the observational data from satellites, from radars, from radiosondes. Radiosondes are weather balloons or weather stations into a weather prediction model, into the physical model, right, to estimate the current state, and then doing the forward prediction.
So I guess it
Um,
sounds like there's a lot of work that needs to be done to actually collect the data for that initial state, feed that data into your
yes.
model, and that there's a lot of like dependence on the initial state. So what it makes me think is the DeepMind paper is really interesting because it's like given radar images, that's the initial
Yeah.
state, and then they use a GAN to generate like what they think what the next state is based off of that like input distribution.
Right. And it's very interesting in the sense that it only uses the radar image as the input and the temporal evolution of the radar image, right? And it is, in a sense, it's making a lot more use of the radar data that's available, which has been really difficult in physical models to really use the radar data adequately. And the success of the prediction of this GAN model really illustrates that there's a lot more information in the radar images that could be extracted for predictive use that we're currently in physical models are not able to extract because of theoretical computational limitations. So meaning partly because we don't have the computing power and partly because we don't understand the processes that lead to precipitation well enough. So a lot of the microphysics that happen in clouds. Right? There's actually a lot of things we don't really understand. And this may be surprising because it's really like classical physics. You would think we could understand this perfectly.
Yeah, speaking of
but it's actually not the
understanding,
case.
I want to make sure that I understand all of these like terms and everything. So this paper talks about nowcasting. So nowcasting, that is predicting the weather now, sort of in the short term. Is that
right?
The right way to think about it? Yeah.
Yeah,
Okay.
yeah. So typically, weather prediction starts sort of at like 6 hours, and that's usually 6 hours. Historically, the assimilation interval where you would reinitialize the model and do a new forecast, and then everything that goes beyond the next 6 hours is you then. Because the initialization is usually a little bit bumpy and incomplete, it needs some time to adjust. And initially, there's like some turbulence, and this turbulence creates precipitation, and that's actually not physically realistic. It's because of artifacts in the initialization, and so then usually for the first couple of hours, the simulation is usually not good, and it creates a lot of noise. And so that's why this nowcasting is not very successful with dynamical physical models, right? But it's very important in aviation, for example, or also just for people. If like you have your radar app, you can look at it on your phone. You can kind of, it tells you if it's going to rain like immediately or soon, right? So you can kind of time when you're going for a run or something, right?
Yeah.
So it's very useful for that, but also for aviation, it's very important, and
So
other traffic.
Yeah, so these
For road traffic and stuff like that.
these models that would do like nowcasting for road traffic and aviation, these would all be like numerical weather models, right? So what we were talking about, Navier-Stokes.
Well, we've been trying to some extent to do this, but there's always been and there are actually also other approaches. So there's a high resolution rapid refresh that the US is running. That's a numerical model that's initialized every hour, and that does have a scheme to assimilate radar data. But this is very new, and it's not perfect. And before that, it was actually mostly the realm of human weather forecasters. So human weather forecasters would look at radar images. They would also look at the numerical model guidance, or guidance is what we say, is the output of the numerical model. And they just look at it and it's sort of saying, okay, I know what the model does and what it's good at, and what it's not good at, and so I'll interpret that. And then I'll look at the radar image and the satellite image, and maybe some wind reports or something. And then a human forecaster would actually make the forecast and so give out warnings, or advise a pilot. So in airports usually have like weather bulletins, right, that they post. And these historically were done by human weather forecasters, by looking at all the information that's available, knowing that the numerical models were not very good at that time scale, and humans were significantly better.
That's so
Whereas for
cool.
longer lead times, that's actually not the case. So if you're looking at like 10 days, you'd almost exclusively rely on the numerical model and apply some like statistical corrections to it,
Hmm.
because humans are not good at forecasting over long lead times. But for short
So it
lead times, you're actually pretty good.
kind of sounds like the DeepMind paper in a sense is automating the work of these human forecasters by
That's
using
right.
radar as the input. Yeah.
Mm-hmm.
And
And
I'm also wondering, so numerical models we've been talking about a lot, but I don't think we've actually defined it. So my understanding of a numerical model is essentially, yeah, Navier-Stokes or some sort of physical model that we solve computationally because there isn't an analytical solution.
mm-hmm.
Does that match your understanding of what a numerical
Yeah,
model is? Okay.
yeah,
And it's
yeah,
very different
essentially,
from
yes.
machine learning.
Yes, right, or statistical models, exactly, yeah.
Mm-hmm.
So a physical or numerical model is different from a statistical or machine learning model.
Yeah. Okay.
Mm-hmm. And
Yeah.
unfortunately, the Navier-Stokes equations don't have a closed form solution
Yeah.
analytically, right?
And then so
Um,
the main difference really between a statistical model and like a numerical model, for me, how I think of it is a numerical model is it's like physics. It's like F equals ma. It doesn't require really like data input, whereas I look at
mhm,
a statistical model or machine learning as kind of like a framework, some sort of function F that we then feed data into, and then it learns a distribution and then essentially
mhm,
learns the
mhm.
model that way.
Right, and so the what I find very interesting about this is that so in environmental science, physical models have been very commonly used, and I think one of the main reasons for this, so they have two advantages, right? One is that they tend to generalize relatively well, because they're based on very general principles, right? Um, they also don't require data for training, for building the model. So in a situation where you don't have a lot of observational data, they can be very advantageous, because you can extract you essentially by writing down the physical equations, you're adding information to the problem, right? And so you don't need to extract that information from the data, so you can really use the data to define your initial conditions,
Mm-hmm.
um, and you can make more use of your limited available data. And so in a lot of environmental problems, and as I mentioned before, in weather prediction, we don't actually have that much data. You may think there are lots of weather stations and radars and satellite observations, but the atmosphere is so large, um, and it moves very quickly, right? So you need to do a weather prediction. You need to know what, if you just want to do a few days, you need to know what the weather is, what the conditions are hundreds of kilometers upstream, right? So the area, the size of the system you need to observe is really large. And this is why, with limited observations, I think physical models have been quite successful because they need less data in this sense, right?
Mm-hmm.
What has changed now is that there have been some observational methods that have generated a lot of data recently, and recently we've developed the ability to process these data. And so radar data is one of those. I mean, weather radars have been around for a long time, but initially they haven't even been digital. Then they've been digitized, but we didn't have the ability to process all of the data. But now we actually do have the ability to process the data. The data is archived. It's a very high frequency, and at this point, we have a long enough record of high frequency, high quality data that has been archived, and the processing power that we can throw data-driven methods at that. There is enough data in some of these cases now, right? But previously, that really wasn't the case. Wouldn't, even if we had the machine learning methods, we wouldn't really have the data to support that.
Yeah, and even in
Except of, yeah,
2015, I remember when I
sorry.
started my master's, I remember asking my supervisor, like, hey, machine learning seems really powerful. Do you think we can do anything here with ML for ocean modeling? And he said, oh, I mean, he's a very well accomplished guy, and I love him very much, but he always said, no, 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 no machine learning. It's absolutely not needed. Um, and I remember just thinking, like, oh, if I really felt compelled, I could have tried to make a case for it, but yeah, it's just very interesting. Like even in the past, like what 7 years, things have changed. Like I think if I sent him an email
Mm-hmm.
now, he would probably say, "Oh, I'm exploring it, or I'm at least open to it."
Mm-hmm. And actually, on a tangent, especially in the in oceanography, a lot has changed with respect to data because now you have the Argo floats, right? There
Right.
there
Yeah.
are automated floats that are all over the ocean, and so not only floats, they also dive, and they are just probing and the ocean everywhere, and they're collecting tons of data now. But this project is only like 10 years old, right?
Yeah.
So it's similar as with the high frequency radar observations that are now widely available. It's something that has only recently become available with a sufficient time series. So one thing that's also important to realize is that for a lot of these data sets, if you start collecting them now, because of the high variability in the atmosphere, you, you you have to wait a couple of years until you have enough samples and as probing enough of the state space, right? That you can actually usefully do something with these data. So it always takes some time until this pays off, right?
hmm Yeah, it's really interesting. So yeah, in terms of like high frequency radar, so the DGMR, so Deep Generative Model of Rainfall, I believe the input radar data, it's every 5 minutes, a snapshot of a radar image over the UK. And then that's
Mm-hmm.
all that can be made into a time series, and then that's fed into some sort of machine learning model that then
Mm-hmm.
learns the distribution of that radar. So yeah, like speaking about the model, so what they use is a pretty standard generative model. So again, Andre, how much do you know about GANs, or how much have you worked with them before?
I haven't worked with them. I know like a little bit. Again, I know roughly what they are, but
Yeah,
no technical detail. Um,
yeah. So are you familiar with this kind of way that people like to think about GANs? It's so a GAN is a generative adversarial network, and you can think of it as like there's a one person who's making counterfeit money, and there's another person who's the policeman trying to determine if this money is
mhm,
counterfeit. So the criminal making the counterfeit money, they would take the role of the generator of the network, because a GAN has two separate networks. Um, and funny aside, my supervisor in my master's is named, his first name is Gan, so I always kind of think of him whenever talking about these. And now we're talking about like numerical weather prediction. Anyways, so yeah, so there's two models, and again, the generator and the discriminator. So the generator is like the criminal, and the discriminator is like the policeman. So the generator tries to, and I'm sticking with like the criminal policeman analogy. So the criminal tries to make counterfeit money that is indistinguishable from real money, and the discriminator becomes better and better at determining if this money is real or fake. So this is what
mhm,
the generator and the discriminator are doing, where the generator is learning a data distribution and is able to make representations and sample from that distribution, and eventually those samples are indistinguishable by the discriminator, and
mhm.
then you have like
Yeah.
perfect, close to perfect representations of like your input data. So that's essentially what the DeepMind people have done here with radar
Mhm.
images.
Right. So yeah, I haven't heard that example before, but yeah, that was roughly consistent with my understanding, but that's about as far as my understanding goes.
Yeah, that's
um,
completely okay.
yeah, and so maybe it would help if we show the audience what these images actually look like.
Yeah, for sure. Do you want to share your screen?
Mhm. I can just share and let's see. Okay.
Yeah, and while you're doing that,
So
so essentially the model is that given n radar fields, given n input radar fields, they predict m future radar fields, and it really is a standard GAN where they're learning some latent variable, latent distributions. You can see here on the left that there are actually two discriminators, because with weather forecasting, it's not too useful to just know like temporally, like in terms of the time series, what precipitation will look like. We actually want to know spatially, like where will that precipitation fall. So that's why they have this radar generator with these two, the temporal discriminator and then the spatial discriminator. And then in terms of technical details, I think these 3 networks are all trained separately, which is pretty standard for GANs. And then there's like a regularization term to apply like a penalty function. And anyway, so this is really the basis of the network. Like looking at it, it seems quite simple to me, but of course, like I think oftentimes like simple solutions are actually very difficult to come up with.
Right. Or just implement.
Yeah,
And
implement.
process
That's
all.
right.
Yeah. And so my understanding is that the basic architecture is similar to what's used for video frame prediction, and in a way you can think of it as kind of something pretty similar. So like a radar, and actually maybe I can show that. So the Environment Canada radar. So Environment Canada has a radar system as well.
Nice. Can you zoom in, please?
Yeah. So you can see some rain here. So Toronto is here.
So using my human judgment, I could say, oh, well, it looks sunny right now, but
Right.
maybe
And
it'll.
so here
Well,
in
actually,
Toronto,
I don't think it's
it
going
is
to rain
sunny.
today.
Right. And there's rain here, and this is the east of here. And so in terms of, you can think of it as a video in the sense that it moves like this, right? So you can see that precipitation systems move, and there's a certain structure to them. It actually has a vertical motion, and yeah, so this is just what it looks like at the moment. So it's over in New York State, I guess. And this is kind of so where the image frame prediction or video frame prediction comes from. Maybe we can look at a longer period as well. This is now over 3 hours, how the precipitation field moves.
Yeah, so essentially we could all do this weather forecasting ourselves as humans by looking at Weather Canada's radar images.
Right. And so, right. So what Environment Canada is showing here on their website is just the observations. So it's just the radar images from the last 3 hours. And then you can play it as a video and kind of extrapolate how it's probably going to move, right? And you can see that there are some structures, and it's kind of predictable how it moves. And you can see how a human forecaster with some experience could do this quite well, right? And so this is in this paper they used radar from the UK, but it's essentially the same type of radar. There's not really any difference. And this is a sample image. So these circles, these are the radii of different radar stations. Right?
Okay.
And then for a prediction, so what we're seeing here is this is like the red box that you saw before, and this is then the actual observations 30 minutes later, and then 60 minutes later, and 90 minutes later, right? So this is the actual evolution of the precipitation field. And so blue is light precipitation, white is no precipitation, and red or yellowish are higher precipitation, right? And then, so the reason why we have, so the thing with the 2 discriminators, one temporal and one spatial, that's, like you said, there's a spatial structure that is important, and that it needs to be spatially consistent as well as temporally consistent.
And how much harder is that to make that prediction? Because I'm just thinking in terms of like, if you think of time series forecasting and then you add an additional dimension to that, I would imagine it would become a much more difficult problem. Do you have any intuition on how much more difficult adding that like spatial component is?
So the interesting thing is, I would say just viewing this as a time series prediction would actually be a lot harder in this case, just because you could see how the system moved, right? So you need the spatial pattern to actually make the prediction for any given point, because you need to know what's coming upstream and kind of know how it moves. If you limit your view to a single point and you try to do a prediction, it's actually almost impossible to do the prediction. Now, in terms of complexity, from a computational point of view, it's probably quite large. But I don't have the. I mean, the resolution of this is quite high, and some of the structures are pretty small. So you probably need that resolution, and so this is 256 times 256 points here. But yeah, so it's hard to quantify that. But I would say it's doing a point prediction as a time series is probably not going to be very successful. But of course, doing the whole spatial prediction is quite complex. It's similar so the numerical weather prediction model is probably more complex than doing this prediction, because it considers a lot more variables and a lot more layering, right?
Yeah. Yeah, like a numerical weather forecasting model, it's really like it's like everything is layered in this grid together to create like a proper spatio-temporal representation, right? Something like that. Like it's rather than this is kind of like just a image snapshot, essentially 2D. Like numerical weather forecasting models, there's like many more degrees to consider, and like it's more difficult computationally.
Right. So the degrees of freedom in the numerical weather forecast are much larger than in this forecast. But it is on a similar, well, it's maybe an order of magnitude or maybe two lower, but significantly higher than a point forecast, obviously.
Yeah, an interesting thing. So I sort of guessed that doing the time series component would be more difficult, but just skimming over the paper a little bit, they add some details where they say that the spatial discriminator itself is a 2D CNN, because with these GANs, you can use any sort of like generative model for the generator, and then I think like any sort of maybe generative or maybe not, maybe any sort of model for the discriminator. So yeah, the spatial discriminator is 2D CNN, I guess X and Y, north, east, southwest, whatever. And it ensures spatial consistency and discourages blurry predictions. So sort of, I think, tries to make sure that the images look real that are output. And then the second discriminator, which is the temporal discriminator, this is a 3D CNN. And I'm thinking this is probably because there's like the X and the Y, and then also the time component. And this specifies that there are, I guess, like temporally consistent images that aren't jumpy, because that would be a pretty poor forecast as well. So it does seem like the temporal part is actually a little bit more complicated, or at least there's like further considerations that they had to implement when building the model.
Yeah, so I would probably agree with that, although I don't know enough about the implementation of the model. But I would agree that temporal consistency is probably the harder part. I could see how, but I mean, for a prediction, it's the more critical part, right?
Yeah, it's really interesting. There was just a question in the chat. So someone asked, so just to clarify, the generator wants to get better so that it can fool the discriminator and make it seem like what was sampled from the generator was real. This is very much like what is happening here. So essentially this, I guess, rainfall radar generator will eventually get so good that it'll output images from here, or from its learned latent distribution, that look like what we're seeing on the screen. Looking at it myself, I sort of think like what is output by DGMR versus the observations, I'm like, I can see some differences. DGMR looks like it's actually a lot more smooth. Like the predictions do look more blurry, I would say, whereas the true observations look a lot sharper.
However, this is already a huge step forward. The true observations definitely look a lot sharper. Now they've compared this to some other benchmark methods that have been used, and so PyStaps. This is a semi-physical approach where you basically just estimating the wind field based on the motion and then extrapolating with some empirical relationships. And that one, because it tends to produce very high precipitation amounts in some areas, and the shape tends to look a bit different, right? It's the reason that it's producing high amounts more often is probably because it's calibrated that way, because you don't want to miss a high intensity event, basically.
Right.
Now, other machine learning methods, this is quite interesting. So you mentioned that the GAN looked smooth, right? So look at the UNet. And then, so the axial attention model that has some kind of convolutional LSTM, I guess. I did not really understand how that one works. The UNet, I have some idea, but these methods look even smoother, and this is often a problem and this has to do with basically the way you train the models in the metrics, right? And something interesting is that, so I've highlighted here in pink and red. These are skill metrics. So CSI is critical success index, and CRPS is continuous rank probability score. So people in machine learning may appreciate this. There has been a lot of work done in numerical weather prediction on skill evaluation of models, numerical and quantitative skill evaluation. And also in hydrology to some extent as well. There's the Nash-Sutcliffe efficiency, NSE, that some people may know. A lot of these are basically variance-based or R-square-based methods. And there's a fundamental problem with R-square-based methods or variance-based methods, right? And that's they penalize outliers a lot, and especially they penalize location errors, right? So if you take, for example, this one here, if you mislocate the precipitation field here, you offset it, maybe you have it here, right? Then that's actually not a horrible forecast, but the RSME or any variance-based method will give you a horrible score. And it will give you a much better score if you just predict an intermediate amount, like an average amount everywhere. You'll get a much better RSME-based score. And this is kind of what these methods do. They just predict a smooth field everywhere and no extremes, because these variance-based methods or R-squared or squared error-based methods really penalize errors or location errors, and they really favor these smooth predictions, like middle of the predictions, right?
That's really
And so
fascinating. How much of a known issue is this in the weather forecasting community?
it's a very well-known issue. Because numerical weather prediction models basically ended up having the same issue. They tend to produce a lot of drizzle. And this is partly because they have lower resolution, and they used to have much lower resolution. But it's to some extent also an outgrowth of trying to optimize metrics, because model developers, metrologists do look at these metrics a lot, and they're competitions for these metrics, right? And it is known that with a smoother forecast, you tend to optimize these metrics. But there's also been a lot of thought about how to solve that problem and to devise metrics that are better. It's just that it seems to be quite difficult. And so there are some that are like the Breer skill score, and so they tend to be more binary, sort of like exceedance thresholds, basically. And this is very similar to the recall and what's used in machine learning. So it's a common problem, and the CSI is a somewhat, it's kind of like a threshold exceedance based score, and the DGMR seems to score better on that. For the ranked probability score, it doesn't seem to work it doesn't seem to do very well, right? So the score is 0.5, whereas the UNet has 0.8. And so they actually did something very interesting in this paper to address this problem, because they're proposing this new method. But if you take a lot of the established metrics, right, it's not doing very well. So are you really better? It looks better, definitely looks better for a human, right? And so they actually went out and polled metrologists, operational metrologists who work in the area, to rate the forecasts.
Yeah, and they call this a cognitive analysis, I think.
Exactly.
Which I thought was quite cute.
Mm-hmm. And so the result was that, as you could guess, experienced meteorologists rate the DGMR forecasts as much better than, for example, the UNet forecasts. And also the PySteps forecast, which is just a traditional advection-based method, gets better ratings typically than the UNet or the axial attention method. So, and then they did another one where, and I'm not 100% sure how they exactly did that, but an economic measure where it's essentially like the rate of false predictions, so and versus the cost of a false prediction, right?
Right, like maybe looking at the cost of closing a airport for some time being, or closing a road,
right.
something like that.
Exactly. Yes. And versus the cost of not closing it and then having an accident, right?
Right. Yeah. There's that other side.
Yes, exactly. And so in this kind of cost-benefit analysis, they also found that the forecasts of the DGMR are significantly better. And so that suggests that it does represent the probability distribution also better than the unit method, for example. And maybe I can stop sharing my screen at this point. If looked at the image enough, I think. So it does seem to learn the distribution a lot more better and a lot more accurately. And the distribution of precipitation is also not Gaussian, right? So, or it's not normally distributed. And so it's much harder to learn for something that tends to be a sort of a smooth square error-based approach, right?
Yeah, and I just wonder, like, looking at all of the images and, there's a human evaluating things. What if we were to get these meteorologists to actually somehow draw and then generate their own predictions based on the radar? Like, what do you think that their predictions, like humans' predictions, would actually look like?
This is actually a very interesting question. I wonder about this too. And I think it depends on the experience of the forecaster, obviously. So for myself, I'm not an operational meteorologist. I would not be able to draw up these kind of predictions with any sense of accuracy. My guess is, and this is sort of an interesting thing that's so similar to the issue with self-driving cars, and that at the moment we have staff meteorologists who have a lot of experience and who are good at this and who can probably make pretty good predictions, even without, or that are comparable to the neural networks. Going forward, when we rely more and more on numerical weather prediction models, as well as these kind of radar prediction models, they will probably get worse at it, the humans, right? Because they just rely a lot more on the technology.
Like worse because they will become lazy and maybe less skilled.
And
I see.
Yeah, exactly. And I think now there are a lot of older meteorologists who have a lot of experience who would be pretty good at this and doing this, because they've just looked at so many of these images. And the human brain is a fantastic neural network, right? And it's not surprising that humans are good at it when they really focus on it. But we have to learn this, right? And when technology can do it for us, we don't learn it anymore.
Yeah,
But
we
then we can do
become
other things,
lazy.
right?
True.
But we
It
can do
opens
other
up.
things, right?
Yeah.
So
Yeah, very much
maybe,
so.
yeah.
Yeah, this is really cool stuff. Unfortunately, we will have to start looking at wrapping up. For everybody who is listening right now, we do have a recipe I think Andre, you put it together with different
Well,
resources.
actually, Amir mostly. So it's
Amir
a
put it
combination
together.
of
Okay.
different recipes. Amir mostly put them together. So I did have some hand in this, but not as much as I should have, I
Okay.
think.
Cool.
I'll, I'd also say some of the recipes do involve, I think there's one with embeddings that's somewhat related, and then another one in downscaling that actually the downscaling one is pretty closely related to this approach, I would say. It's a different application, but technically it's similar. We do have another one which is on the convection forecast or convection parameterization, which is maybe more of an alternative method to this. So there's this one predicts just from the radar images, right, as we've discussed. But then there's this whole area of numerical weather forecast that physically simulates all these processes, right? And so there's a lot of machine learning is used or is starting to be used in a lot of different areas, right? There's this kind of prediction is basically a prediction where it's quite it's very specific, and it's only forecast. It's outside of a numerical model, right? But then there are also processes inside numerical models. So yeah, this one is it's a standalone prediction, right? It works with radar, and it
That's
learns
right.
the physics to the extent that it has to, and it makes a prediction about something very specific. There are also processes in numerical models that are not very well understood. Like I mentioned, for example, cloud microphysics, where as we are collecting more data, but also doing more numerical simulations, neural networks can be used to in tandem with numerical models or dynamical models to represent processes in like turbulent small-scale processes in numerical models that are otherwise hard to represent, right? And so we have one about those as well that relates more to long-range weather forecast, especially, and it's especially actually looking at precipitation because that's one of the most difficult processes. Right? But there's like a whole range of different ways that machine learning can be applied, and yeah, it's a really interesting space.
Yeah, that's awesome. So there's your call to action, everybody. If you're interested in learning about different ways
Mm-hmm.
machine learning can be applied to climate modeling and weather forecasting, go check out the recipes. I would say so. My takeaway from this paper, at the end of it, in their conclusion, they say something like the prediction of heavy precipitation at long lead times is difficult, um, or remains difficult. Blah blah blah, whatever. I would really love to actually look at how physical models do actually solve this. I haven't spent time looking at it. And just whenever I think about like long lead times, my mind does switch to like physical models because I know they take quite a while to spin up. So,
Mm-hmm.
anyways, so my overall conclusion is just that this seems like a very interesting paper. I love that they use GANs. I love that they adjusted GANs to like the spatial temporal necessities of climate modeling, but I still feel like I guess my love for physical models is still there. Like I would want to see how physical models can do
Mm-hmm.
this, or yeah, how the two like perspectives and methods can be unified. What about you, Andre? What's your takeaway?
Yeah, well, I think what they meant by long lead times here is 6 hours,
Okay.
like long lead time for the radar. But my personal interest is also more in what is actually long lead times, which is like 10, 30 days, something like that. So I totally agree with you on this. But I don't think physical models really will go away because I mean, there's no reason to throw out something that we do understand well, and there are things that we understand well, and that are very successful. So I think the future is really going towards hybrid approaches, where components in models, especially for longer lead times, that are hard to represent or very expensive to simulate. Right? So if you're thinking of very long lead times, seasonal forecasting, which is a very interesting area, you have to run the models for really long times. And then the numerical or the computational performance becomes very important. And you have to approximate a lot more processes. And then machine learning can really help. And you can train these machine learning algorithms on the output of higher resolution short-range models. So this is a very interesting option. And also an interesting area is, of course, to bring more physics into these machine learning models, right? So in the radar image case, they did not really enforce any physics except for that it has to look realistic. That does enforce some physics, but the information that the model is getting from the radar image alone is actually not enough to really sufficiently constrain physics, really. Like energy conservation, you don't actually know how much energy is in the system by just looking at the radar image, right? Because you would need to know what the humidity and temperature is and all of this, right? So energy conservation based on radar images doesn't actually work. It does work, so in numerical dynamical models. They have full energy conservation. You can enforce energy conservation there. And for example, in the precipitation convection parameterization case, you can enforce mass conservation, energy conservation, and momentum conservation. And that actually makes simulations more stable. So there's a tangible benefit to doing that. Because if you don't do that, they do have a tendency to explode. So the model just generates, it just adds more energy to the system. So this is in the hybrid modeling approach. I think physics-informed machine learning and physics-constrained machine learning is really interesting and really important to keep the models stable and consistent. And this is like for me. It's more for the long-range forecasting, but it's the area that I personally also find more interesting. Whereas I think the radar image, this is more of, it's something that lends itself more to really data-driven approaches.
Right. Yeah, as opposed to physics-informed ML. Well, I guess we have a topic for potentially next time. Yeah, thanks so much, Andre, for joining. Thank you, everybody, for joining, and check out the recipes.
Yeah, thanks. It was a pleasure to talk. And unfortunately, Amir couldn't join us. That would have been interesting too. I know he likes to talk about physics-informed ML.
His physics perspective. I mean, he's there. He's the man behind the curtain, literally.
All right.